Welcome back to GeoMethod channel. In this video, we solve the same area equals perimeter right triangle problem using method 2, Euclid Parametrization. This is method 2, same problem as we had shown before. Find every integer right triangle whose area equals its perimeter. In method 1, we solved it by direct factoring of area equals perimeter after eliminating c from Pythagoras. This time, we take a different route. We use Euclid's parametrization of every integer right triangle and let area equals perimeter collapse to a tiny product. Before diving into algebra, let us warm up with a few familiar small integer right triangles and see how each one behaves under the condition. Start with the smallest one we all know, 3, 4, 5. Its area is 6 and its perimeter is 12, not equal. A miss, but it sets the scene. Now try the next familiar triple, 6, 8, 10. Its area is 24, and its perimeter is also 24. They are equal, so 6, 8, 10 is our first solution. A nice early win. And one more, 5, 12, 13. Its area is 30, its perimeter is 30, both equal. That is already 2 solutions from just 3 small attempts. With a hit rate that high, it is natural to ask, are there many more solutions, perhaps even infinitely many? But there is a clean reason to expect only a handful of solutions. Area is a product, roughly a times b over 2, which is quadratic in the leg lengths. Perimeter is a sum, just a plus b plus c, which is linear. As a or b grows, area races past perimeter very quickly, so equality has very little room. The solutions, whatever they turn out to be, are almost certainly limited. Our task from here on is to pin them down exactly. We will derive a theorem, starting from Pythagoras, that generates every integer right triangle, and then use it to catch every solution. Place the history carefully. Plimpton 322 is an early Babylonian table of examples of Pythagorean triples, not a solution to our problem. Euclid is the key source for this lecture, because Euclid gives the parametrization that classifies primitive integer right triangles, and then scaling gives all integer ones. Diophantus is later number theory context, relevant because he studies integer and rational solutions, but not the tool we use here. And much later, Fermat proposed that if the exponent is bigger than 2, then there are no positive integer solutions at all. Our problem stays in the exponent 2 world, where infinitely many Pythagorean triples exist, and asks which of them also satisfy area equals perimeter. Now we derive Euclid's formulas. Start again from Pythagoras. Move integer a squared to the right. B squared equals c squared minus integer a squared. Factor the right side as c minus integer a times c plus integer a. We work with a primitive triple, meaning the greatest common divisor of integer a, b, and c is 1. Now check the parity of integer a and b. There are 3 cases, both legs even, both legs odd, or exactly one of each. Under primitivity, cases 1 and 2 both collapse. We will rule them out next. Case 1. Both integer a and b are even. Then 2 divides c squared, so 2 divides c. That forces 2 to divide the greatest common divisor of integer a, b, c, but we assume the triple is primitive. Greatest common divisor equals 1, contradiction. So case 1 is ruled out. Before the second case, recall the following identity. Any odd integer equals 2k plus 1, squaring and expanding, 4k squared plus 4k plus 1, reducing mod 4, only the 1 remains. So every odd square is congruent to 1 mod 4. Now assume both integer a and b are odd. Then integer a squared and b squared are each 1 mod 4, so their sum is 2 mod 4. But c squared can only be 0 mod 4 if c is even, or 1 mod 4 if c is odd. 2 is neither. Contradiction. So the both odd case is also ruled out. Cases 1 and 2 are ruled out, so exactly one of integer a and b is even. Without loss of generality relabel, so integer a is odd and b is even. Then c squared equals odd plus even equals odd, so c is odd. And c minus integer a and c plus integer a are both even. If D divides both halves, D divides their sum C and their difference integer A. But the triple is primitive, so greatest common divisor of integer A and C is 1. Therefore, D is 1. We need a classical number theory lemma. If U times V is a perfect square and U and V are coprime, then U and V are each perfect squares. The proof is unique prime factorization. A prime appearing in U cannot appear in V, so its total exponent in k² equals its exponent in U alone, which must be even. Apply the lemma. The product of the two halves is b over 2, all squared. They are coprime, so each is itself a square. Call them n² and m². Adding and subtracting the two equations recovers integer a equals m² minus n² and c equals m² plus n², and b over 2 is mn, so b is 2mn. That is Euclid. For a non-primitive triple, let k be the greatest common divisor of a, b, and c. Dividing through gives a primitive triple that still satisfies Pythagoras because the relation is homogeneous. By what we just proved, every primitive Pythagorean triple takes the Euclid form. Multiplying through by k recovers the general parametrization. Integer a equals k times m² minus n², b equals k times 2mn, c equals k times m² plus n². Euclid's parametrization. Every integer right triangle has sides integer a equals k times m² minus n², b equals k times 2mn, c equals k times m² plus n². The parameters are k greater than or equal to 1, m strictly greater than n greater than or equal to 1, greatest common divisor of m and n equal to 1, and m plus n odd. Each integer right triangle appears exactly once, as k, m, n vary in these ranges. Recall, the factored identity from method 1 still mixed all three variables. Euclid reduces 3 unknowns to 3 parameters, still 3, but with tight constraints that make classification possible. To hit every integer right triangle exactly once, k at least 1, m greater than n at least 1, greatest common divisor of m and n equal to 1, and m plus n odd. Integer a² plus b² expands to k² times m to the fourth plus 2m² n² plus n to the fourth, which is k² times m² plus n² equal to c². We require k at least 1, m strictly greater than n, coprime, and of opposite parity. If d divides both m and n, then d² divides a, b, and c, so we could absorb it into k. Coprimality ensures each primitive triple appears exactly once. If m and n are both odd, then m² minus n² and 2m, n are both even, so a, b, and c share the factor 2. Forcing 1 even makes the output primitive. K is simply the common scaling factor. If k equals 1, the triple is primitive. Otherwise, k equals the greatest common divisor of the three sides. Every integer right triangle corresponds to exactly 1k, m, n under these rules. Classifying triples reduces to classifying triples of parameters. With m2, n1, k1. Integer a equals 4 minus 1 equals 3. b equals 2 times 2 equals 4. c equals 4 plus 1 equals 5. Greatest common divisor of 2 and 1 is 1, and 2 is even. Pythagoras, 9 plus 16 equals 25, which is 5 squared. With m3, n2, k1, integer a equals 9 minus 4 equals 5, b equals 12, c equals 9 plus 4 equals 13. Keeping m and n, but setting k to 2 scales the sides by 2, producing 6, 8, 10. Its greatest common divisor is exactly 2, matching k. If m equals n, the strict inequality fails and it collapses to 0. The conditions are not cosmetic. Taking m3, n1, both odd, produces 8, 6, 10, which is 2 times 3, 4, 5 with legs swapped. The parity rule blocks this duplicate. Area is 1/2 times k times m² minus n² times k times 2mn. After simplification, area equals k² times mn times m² minus n². Factor m² minus n² is m minus n times m+n. So area equals k² times mn times m minus n times m+n. Perimeter equals k times m² minus n² plus k times 2mn plus k times m² plus n². The n² terms cancel, leaving k times 2m² plus 2mn. Factoring out 2km gives p equals 2km times m plus n. So p equals 2km times m plus n. Ready to equate with area. Area equals perimeter becomes k² times mn times m minus n times m plus n equals 2km times m plus n. Divide by km, which is positive, giving k n times m minus n times m plus n equals 2 times m plus n. Cancel m plus n to collapse the equation to kn times m minus n equals 2. So, three positive integers k, n, and m minus n multiply to 2. Since m is greater than n, m minus n is at least 1. Algebra collapses to kn minus n equals 2. Now enumerate factorizations. Three positive integers k, n, and m minus n multiply to 2. The three ordered factorizations are 2, 1, 1, 1, 2, 1, and 1, 1, 2. These give the three candidate assignments for k, n, and m minus n. In the first case, k is 2, n is 1, and m minus n is 1, so m is 2. Integer a equals 2 times 4 minus 1 equals 6. B equals 2 times 4 equals 8. C equals 2 times 5 equals 10. Case 1 produces the triangle 6, 8, 10. Case 2. K equals 1, n equals 1, m minus n equals 2. So m is 3. Integer a equals 9 minus 1 equals 8. B equals 2 times 3 equals 6. C equals 9 plus 1 equals 10. Case 2 yields 8, 6, 10, which is 6, 8, 10 with the legs swapped. Case 3. K equals 1, n equals 2, m minus n equals 1, so m is 3. Coprimality and parity check. Integer a equals 9 minus 4 equals 5. B equals 12. C equals 9 plus 4 equals 13. Case 3 produces the primitive triangle 5, 12, 13. 6, 8, 10 and 8, 6, 10 share the same side multiset. Swapping integer a and b just relabels the triangle. After quotienting by leg swap, only 6, 8, 10 and 5, 12, 13 remain. 6 squared plus 8 squared equals 100 equals 10 squared. Area and perimeter are both 24. 5 squared plus 12 squared equals 169 equals 13 squared. Area and perimeter are both 30. Both triangles pass the condition, and the tiny product reduction rules out everything else. A primitive integer right triangle has no common factor among its three sides. 6, 8, 10 has greatest common divisor 2, so it is 2 times 3, 4, 5. 5, 12, 13 has greatest common divisor 1, so it is primitive. Under the primitive restriction, only 5, 12, 13 survives. The question asks for all integer solutions. The complete answer is 6, 8, 10, and 5, 12, 13, up to leg swap. A variant of the question asks for all primitive integer solutions. In that case, only 5, 12, 13 satisfies coprimitivity, since greatest common divisor of 5, 12, 13 equals 1, while 6, 8, 10 has greatest common divisor 2. It turns out that in ancient Greece, mathematicians like Euclid already studied this special integer case for right triangles and gave beautiful classifications. Method 2 inches this lecture series uses their parametrization to reach the same answer by a different route. Notice something. We started with what looked like a geometry question, triangles, area, perimeter, but the moment we required a, b, and c to be positive integers, the problem stopped being about shapes and became a number theory problem. The substitutions, the factoring, the parametrization, all of those are number theory tools. The integer constraint is what forced the shift. Hope you like the solution, and take a moment to appreciate what ancient mathematicians like Euclid gave us. By finding a clean reparametrization of every integer right triangle, they turned a hard integer question into a small factorization and advanced number theory, analysis, and algebra at the same time. The same style of reparametrization trick still shows up in modern mathematics today. So the next time you see an integer right triangle, you will know that Euclid's parametrization is in your toolbox. Every such triple has the form A equals k times m² minus n², B equals k times 2mn, and C equals k times m² plus n², with k at least 1, m greater than n, co-prime, and one of m, n even. Thanks for watching. If you like this channel, please click like and subscribe to see more videos like this. Leave a comment if you have any questions.